So I'm Aditya from University of Mainz, and today I would like to talk about exchange bias in FGT MnPS3 van der Waals heterostructure and how we can manipulate it. So before we get into the talk, I would like to thank all the people involved in this project and our collaborators from different institutes in Austria, Germany, and China. So now I would draw a brief outline of the talk. So I would start with the brief introduction to concept of exchange bias and why we want to use van der Waals materials for it. And then I would look into it, the origin of exchange bias in this heterostructure. After that, we would see how thermal cycles can manipulate the exchange bias. And finally, we would discuss the conclusion. So first of all, what is exchange bias? So if we have a ferromagnet and antiferromagnet van der Waals or any kind of heterostructure, the spins from antiferromagnet would couple with the spins of the ferromagnet. And because of this, the ferromagnet would experience a net field in a certain direction. And since antiferromagnets are much harder to switch, this field would stay constant when you do the hysteresis loop of your ferromagnet. And this will appear as a shift in a negative direction. So if the experience field is positive, you see the shift towards negative direction, and vice versa. So if the experience field is negative, you see the shift towards positive direction. This shift in hysteresis is called exchange bias, and you can just quantify it by taking the sum of two coercive fields. So the concept of exchange bias is not new. It has been there for decades. In fact, it was discovered in 1956 by John and Bean in cobalt oxide nanostructure, core shell structures. Since then, this field has been growing consistently. The number of publications each year have been increasing, and the credit of that goes to the applications of this field has found in memory devices. For instance, magnetic tunnel junctions have a reference layer which uses exchange bias to stabilize it. Even this field field of exchange bias is very established and has applications. The underlying mechanism is still not unambiguous. There are a couple of models who try to explain exchange bias by explaining the exchange coupling between the nearest spins across a flat interface. But we know if you're fabricating a thin film or core cell structure, there would be a lot of defects. Defects such as interfacial stress, interfacial roughness, there could be interdiffusion of atoms. And if you have a polycrystalline sample, you could have different crystallographic orientations and various grain boundaries. So these defects are very hard to quantify, and because of that, it becomes very difficult to compare the experimental results with the existing models. And that's where 2D materials comes in. 2D materials have this intrinsic layered structure, so you would have one layer of atoms, then a van der Waals gap, and another layer of atoms. And when you stack them, you have a possibility to form a completely flat interface. And because of this property, they offer a perfect platform to study interface-related phenomena. So this field has been very active in the past decade. Many people have studied exchange bias with various different ferromagnets and antiferromagnet combinations. And I have tried to summarize some of them here with van der Waals ferromagnet and antiferromagnet. But surprisingly, there are also few works which show exchange bias when your antiferromagnet is fully compensated. What do I mean by that? It's just that the one layer of the antiferromagnet is compensated in itself. So if you look at the exchange coupling from this spin, it would cancel out the exchange coupling from this spin. So the net exchange coupling should be zero. So the system should ideally could not give any exchange bias. In thin film systems, it's okay because you have defects. So even though your antiferromagnet is supposed to be ideally compensated, but in practical it's not, and you can get the exchange bias. However, in 2D materials, it becomes complicated and it's hard to explain if you're assuming a flat interface. So we did that. So we basically fabricated a van der Waals heterostructure with iron germanium telluride and MnPS3. And MnPS3, the antiferromagnet we chose, is a C-type antiferromagnet, which means one layer of atoms would be compensated in itself. The ferromagnet we chose, FGT, also has a similar outer plane anisotropy, and it's conductive in nature. So because of that, we can just do anomalous Hall effect measurements to probe the hysteresis. So we did that at different temperatures and plotted the data against temperature. So we observed a huge magnitude of exchange bias. It's close to 150 millitesla exchange bias. So if you look at the recent works, the magnitude of exchange bias is quite high. And there are two interesting things about this. First, we expected a fully compensated interface. So why we are getting such a huge exchange bias? And the another point is, this exchange bias is disappearing way below the Néel temperature of MnPS3. So Néel temperature is around 78 Kelvin, and we see that the exchange bias just disappears around 40 Kelvin. So what's happening here? So it's possible that maybe since the spin flop field, where MnPS3 goes from out of plane to in-plane antiferromagnet, could have some canted moment, which can eventually pin the spins of the ferromagnet, and that could induce exchange bias. But this kind of spin flop coupling cannot induce unidirectional anisotropy. It only induces uniaxial anisotropy. That basically means it can only increase the coercivity of the hysteresis and should not induce exchange bias. So what's happening here? To thoroughly check this, we decided to do characterization of MnPS3 bulk crystal. So we did that, and if we look at the squid data, we see emergence of anomalous ferromagnetic moment below 40 Kelvin. And if you look at this field sweep, we see that this magnetic moment is indeed ferromagnetic. So basically, at below 40 Kelvin, MnPS3 goes through a spin reorientation transition and shows some anomalous ferromagnetic moment. This kind of spin reorientation transition in MnPS3 has also been reported in 2 recent works here. But now to check if this spin reorientation transition also persists in a nanoscale flake that we use for our heterostructure, we collaborated with the University of Basel and did NV magnetometry measurements. So here we could plot the stray field from this weak anomalous ferromagnetic moment, and we could see that if we change the field to change the sign of the field, the stray field changes sign, which basically means magnetization is switching, which confirms that there is also some ferromagnetic moment in this nanoscale flake. So what's happening here is that this ferromagnetic moment that emerges below 40 Kelvin in MnPS3 is spinning the magnetic moment of FGT and induces this huge exchange bias. So once we know that where the exchange bias is coming from, we can get into the manipulation part. So in a conventional thin film system, we induce exchange bias by doing something called field cooling. So field cooling is where we heat up the sample above the Néel temperature of the antiferromagnet, and then we apply the field, and then we cool down. So this allows for a preferred orientation of the antiferromagnet so that it can give maximum exchange bias. This method is highly reproducible if you're working with thin films. However, in our case, we did it for 3 times, and we could see that the magnitude of exchange bias was varying. It was evolving. And what could be, I mean, it's just few measurements, so you might say there is some measurement artifact that's not perfect. So we did it 15 more times, and we could still see that the magnitude of exchange bias changing. It's constantly evolving. So probably it's just one bad sample. So we did for 2 more samples, and we could see that this magnitude of exchange bias keeps on varying if you do thermal cycling. So what's happening here? There was a recent work which showed if you laser shock a van der Waals heterostructure, where you're heating up the heterostructure, and these 2 materials that we have here would have different thermal expansion coefficient. So if you're heating them fast, there would be a large interfacial stress because of the mismatch in thermal expansion coefficients. And this interfacial stress would change the van der Waals cap. And once you change the van der Waals cap, this changes the exchange coupling energy, and this could eventually change the exchange bias. So is this something that could also be happening in our system? To check that, we collaborated with Forschung Zentrum Jülich, and we did high resolution scanning transmission electron microscopy. Surprisingly, what we saw in our interface was that the interface is not exactly flat. We still see some amorphous region. So, but we did not really expose our sample to the air. So what's happening here? So if we look at the elemental analysis of the interface, we see that the iron, you can see the germanium atoms are going through the MnPS3 layer, and same for phosphorus layers are interdiffusing into iron germanium telluride. So the 2 layers of FGT and MnPS3, when put close together, they can interdiffuse, and that would depend on the chemical stability of this interface. So even though on their own, and if there is no air, they are stable, but if you put next to each other, they can react and cause interdiffusion and form amorphous region. So, but can this amorphous region change when we are heating, cooling, and can this change the exchange bias? So we quantified it. So we basically now started looking at the intercrystalline distance between the 2 layers. When we do it, we can look at the distance between 2 crystalline regions, and we heat it, cool it. We did it a couple more times, and we could see that this intercrystalline region is constantly is changed in last 2 cycles. This confirms that if you're heating cooling, this intercrystalline distance can change, and this can eventually change the exchange bias. So now it basically explains that when you're heating cooling a cycle, you can have some interdiffusion, and if you are doing it multiple times, the state can change and modify various interface related phenomena. And this is what reflects in our exchange bias measurements. So just doing thermal cooling cycles modifies the intercrystalline distance, and we see change in exchange bias. With that, I would like to thank you for your attention. I would like to thank various funding agencies for supporting our work. And now I can conclude. So in summary, I first showed you that our FGT MnPS3 heterostructure could show huge exchange bias despite having compensated interface, because at low temperatures goes through a spin reorientation transition. And this creates some anomalous ferromagnetic moment, which eventually gives you this huge exchange bias. Then we showed that 2D materials do not always form pristine interfaces. There could be interdiffusion of atoms, which can form an amorphous region at the interface. And this region could vary if you do heating cooling cycles. And this could modify the interface related phenomena. In conclusion, we also make clear that to understand the coupling of van der Waals layers, interface characterization becomes of key importance, as the interface in van der Waals heterostructure are not as pristine as we would expect them to be. So thank you. And if you want to look at the paper, here's the QR code that you could scan. Thank you. Now I'm open to questions.
Thank you, Aditya, for your amazing presentation. It was very concise and clear.
Thank you.
The audience, do you have any questions regarding this presentation? Yes. Yes, Mahmoud, you can go for the question.
Yeah, 100 millitesla exchange bias field is a very good, actually very good. If also this can go for application like MTG and so on, but unfortunately it's quickly vanish around 80 Kelvin.
Yes.
So what
Yes.
Can you comment to something?
Very, very interesting point. So indeed, since these materials are only active at very low temperatures, the magnitude of exchange bias is not really useful for the applications. But the interesting part here is exchange bias is a very interface-led phenomena, and it kind of gives you a way to study the interface. So the idea of our study was not to just look at exchange bias that we can use for different applications. The idea was to check what is the interface. Like it's a question in the in the literature that if 2D materials are forming a flat interface, why are we getting exchange bias? So the purpose of the study was to explore that. And we showed that this is happening because of the spin reorientation transition, and it is also possible that the interface is not really clean.
Okay, thank you.
Yeah.
Okay, great. Yeah, thank you, Aditya, for the presentation. If you have other questions, you can ask them at Qatar Town when we meet later for the poster session. Thank you again, Aditya.
Thank you so much, Nabil.